Per-frame template matching is a widely adopted methodology for visual object tracking, which has demonstrated success in accurately estimating the location of a target in every video frame, leveraging its initial state. However, this approach overlooks the inherent temporal dependencies present in video frames. It is evident that incorporating ample temporal data can significantly enhance the accuracy and robustness of a tracker. Humans, for instance, leverage temporal information to perceive changes in a target's deformation, velocity, and acceleration trends, enabling consistent tracking results even when visual information is indiscriminate or temporarily unavailable. Expanding on the aforementioned concepts, our proposed method, AR-Track, leverages spatiotemporal prompts to capture the sequential evolution of object trajectories across frames. Unlike traditional approaches that involve customized heads and post-processing techniques, AR-Track simplifies the tracking pipeline by directly regressing coordinates, resulting in state-of-the-art performance. Per-frame template matching is a widely adopted methodology for visual object tracking, known for its success in estimating the location of a target in each video frame based on its initial state. These methods typically comprise three key stages: 1. Deep neural network-based feature extraction, 2. An integration module for feature matching, and 3. Bounding box localization accomplished through a customized head. However, the incorporation of intricate and redundant manual design modules presents challenges in optimizing the model for edge devices and undermines the overall simplicity of the model. The use of customized heads and post-processing techniques introduces complexity and a need for individual training, thereby compromising the end-to-end framework. Furthermore, per-frame template matching overlooks the significant temporal dependencies present among video frames. It is evident that incorporating abundant temporal data can greatly enhance the accuracy and robustness of a tracker. Humans, for example, leverage temporal information to discern changes in a target's deformation, velocity, and acceleration trends, enabling consistent tracking results even in the presence of ambiguous or temporarily unavailable visual information. In this paper, we present AR-Track, an autoregressive framework designed to address these limitations. Instead of relying on template matching, we approach tracking as the task of interpreting a sequence of coordinates. To overcome the challenges posed by customized heads and post-processing, we adopt a simple encoder-decoder architecture, which enables an end-to-end framework. To harness the potential temporal dependencies among video frames, we introduce a novel method that models the sequential evolution of object trajectories across frames. This is accomplished by iteratively decoding the entire trajectory sequence, utilizing the previous outcomes as spatiotemporal cues. Notably, our proposed method, AR-Track, is trained using a structured loss function that unifies the task objectives for both training and inference. As evident from our approach, we formulate tracking as a time autoregressive process. We introduce a tracking framework named AR-Track, which comprises the following key components: sequence construction, network architecture, and objective function. For sequence construction, we employ a discretization approach to represent continuous coordinates, eliminating the requirement for a large number of parameters. Each coordinate is discretized as an integer value within a specified number of bins. To establish a unified representation, we map the bounding boxes from different frames onto a common coordinate system. This is achieved by storing box coordinates in the global coordinate system for preceding frames and subsequently transforming them to the current coordinate system. Additionally, we extend the representation range by scaling it with a multiple of the search region range. The AR-Track architecture consists of an encoder and a decoder. The encoder is a general image encoder responsible for encoding pixels into hidden feature representations. In our implementation, we adopt the VIT encoder, which unifies feature extraction and integration. To interpret the coordinate sequence, we employ a transformer decoder. This decoder progressively decodes the entire sequence, conditioning its predictions on preceding coordinate tokens serving as spatiotemporal prompts, a command token, and visual features. The decoder effectively incorporates spatiotemporal information and combines motion cues with visual cues to provide comprehensive predictions. AR-Track is trained on video sequences, surpassing per-frame training in optimization. To accomplish this, it employs a structured objective that maximizes the log likelihood of token sequences, utilizing a softmax cross-entropy loss function. Additionally, we introduce the SIOU loss to enhance the spatial correlation assessment between predicted and ground truth bounding boxes. This involves leveraging the distribution's expectation to express the coordination, deriving the predicted bounding box, and computing its SIOU with the ground truth. In contrast to traditional per-frame training that incorporates random translation and scale transformations for the ground truth to simulate spatial dithering, our sequential training follows a different approach. We interpret a sequence of coordinates that trace the target frame by frame without any augmentations. By adopting this method, our model is able to capture potential temporal dependencies through sequence-level objectives. We conducted extensive experiments, demonstrating that the simple and elegant ARTrack architecture achieves state-of-the-art results on popular tracking benchmarks, including GOT10K TrackingNet LASOT extension. The outstanding performance of ARTrack on these datasets indicates that it surpasses customized trackers. While the ARTrack framework offers promising performance, it suffers from a notable limitation in terms of computational efficiency compared to recently proposed trackers, primarily due to its serial computation in the decoder. To address this concern, we explored an alternative decoder architecture consisting of stacked self-attention and cross-attention layers. In this altered decoder design, multiple self-attention layers process coordinate tokens in an autoregressive manner, while parallel cross-attention layers aggregate visual features. This modification significantly improves the inference speed of the tracker, resulting in a remarkable 73% speedup. However, it is important to note that there is a slight trade-off in accuracy, with a marginal decrease of 0.3% on the AO score. To provide further insights into our time autoregressive model, we present frame-by-frame cross-attention maps generated by ARTrack and compare them with the attention map estimated by OSTrack. In challenging scenarios involving occlusion and distraction, per-frame template matching often proves to be unreliable. Occlusion can cause the target to become invisible, while the presence of various similar objects in the scene can confuse the tracker. Remarkably, in each of these scenarios, our tracker consistently focuses on the relevant extremities when predicting each coordinate, showcasing the model's exceptional ability for precise localization. As a conclusion, we propose ARTrack, a simple and straightforward end-to-end autoregressive framework for visual object tracking. Our approach treats visual tracking as a task of interpreting a sequence of coordinates and leverages language modeling to simultaneously perform visual template matching and motion information modeling. The ARTrack architecture is based on a general encoder-decoder framework, eliminating the need for customized heads and post-processing, which streamlines the tracking pipeline. Additionally, we introduce spatiotemporal prompts that capture the sequential evolution of trajectories, enabling the propagation of motion cues for more consistent tracking results. Extensive experiments validate the effectiveness of our tracker, surpassing other mainstream approaches and achieving state-of-the-art performance on established benchmark datasets. Thanks for your listening.